Hi, this is Dinesh from Pristine. In this video, we will look at exponential distribution. So far, we have looked at a few discrete distributions like Poisson, negative binomial, and binomial, which are used to model frequency of operational losses. That is the count of losses during a time period like 12 months or a quarter. Now we will look at a few continuous distributions like exponential, variable, gamma, log normal, and GPD, which are used to model severity of individual losses. Now remember, it is the severity of an individual operational loss. When we combine these two distributions, that is the distribution of number of losses and the amount of individual losses, we get the total loss distribution. Operational VAR is nothing but a quantile of the total loss distribution. Usually the quantile will be 99.9%. So we start our videos on continuous distribution with the exponential distribution. Now exponential distribution is a fairly simple distribution in the sense that it can be parameterized using only a single parameter. So just like we had Poisson distribution in case of frequency, which was a single parameter distribution, exponential in case of continuous distribution is a single parameter distribution. Exponential distribution is nothing but it describes the time between events in a Poisson process. Therefore, between two events in a Poisson process, the inter-arrival time is exponentially distributed. The PDF is lambda e minus lambda x, where lambda is the single parameter which is used to define exponential distribution. In case of exponential distribution, mean is equal to standard deviation is equal to 1 by lambda. Also, the distribution has a constant shape. That is, the exponential distribution cannot assume different shape to fit different type of data set. By shape we mean that the distribution has a constant skewness of 2 and a constant kurtosis of 9, that is an excess kurtosis of 6. With a constant skewness and kurtosis of 2, 6, the histogram of an exponentially distributed data set will always look like this. Okay. The distribution per se cannot change in shape to something like this to fit a different kind of data set. So an exponential distribution in operational risk is rarely a good fit to practical data set. This is because the distribution cannot assume more than a particular shape. Also, it is categorized as a thin tail distribution. So in practice, the distribution does not provide a good fit to the real life data sets. Now we will look at a small caselet on exponential distribution. Say we fit exponential distribution to a particular loss severity data, and we find that the following are the moments of the underlying data. Mean is equal to 4.97, standard deviation is equal to 4.98, skewness equal to 2, and kurtosis equal to 9.54, that is an excess kurtosis above the normal distribution equal to 9.54 minus 3 is equal to 6.54, because we know that the kurtosis of normal distribution is 3. Now even without doing the distribution fitting exercise, we can see that exponential will be a very good fit to this data set. This is because mean is equal to standard deviation and the skewness kurtosis of the underlying data is close to 2,6. Now let us see, if we fit exponential distribution to this data set, what will be the worst 95 out of 100 loss event? What will be the worst quantum? If there are 100 loss events in a particular year, what will be the worst case loss amount in 95 out of 100 cases? Essentially, we just have to find out the 95th quantile of the exponential distribution. In Excel, however, the inverse function of exponential distribution is not available. So we will use the cumulative function. We use exponential distribution function. We select the loss amount, which is nothing but x. Lambda is nothing but the rate or this parameter of the exponential distribution. And we take cumulative equal to true. Now we can see that the 95th cumulative probability is very close to a loss amount of 15. So if we just change it to say a number like 14.9, the cumulative probability is very close to 95%. Therefore, the maximum amount of an individual loss in 95 out of 100 cases will be equal to 14.9. Now if we look at the shape which can be assumed by exponential distribution, if we change the scale parameter to any number, we can see that the shape of the distribution does not change. The shape of the distribution remains the same. Few software uses a rate parameter. Few software use a rate parameter which is nothing but inverse of the scale parameter. So if we know scale, we know rate, and rate will be nothing but equal to 1 divided by scale. So if we change the scale parameter, we can see that only the dispersion of the distribution changes, but the shape and the location does not change. Now let us look at this summary of Bank of Italy 2002 loss data collection exercise. Can we conclude that exponential distribution will be a good fit for any of the business lines? Now we can see across all the business line there is a large difference between mean and standard deviation. Also the data is heavily skewed and it has very high kurtosis. That means data is fat-tailed and very highly skewed. Therefore, a simple distribution like exponential, which has a constant skewness kurtosis of 2,6, cannot provide a good fit to this type of data set. Therefore, exponential will only be a good fit if histogram of the data set looks something like this, and if the skewness kurtosis of the data is close to 2,6 and mean is equal to standard deviation. In the next videos, we will start looking at two parameter distribution. The two parameters could either be location and scale, or scale and shape. Distribution in this family will be Weibull and gamma. distribution in this family would be log normal. And then we will look at a distribution which has all the three type of parameter, which is GPD. Thank you.